Modern engines are becoming smaller and yet more powerful. One of the systems that enables this is variable valve timing. The schematics and procedures used in this video are typical of most vehicles. Always refer to the manufacturer's specifications before commencing any work. The purpose of variable valve timing, or VVT, is to allow the vehicle's engine to operate more efficiently throughout its power range, increasing low-speed torque and high-speed performance while decreasing harmful emissions. On some engines, VVT has eliminated the need for exhaust gas recirculation valves. This is not possible in an engine with a fixed position camshaft. The common types of VVT in production vehicles today are cam phasing, cam changing, multi-displacement and active fuel management systems. In this video, we will cover cam changing. These systems are usually actuated by the Engine Control Module, or ECM. Cam changing can also be described as cam staging. Most stage systems allow for two different valve timings and valve lift settings. These systems switch between two or more differing camshaft load profiles based on operating conditions. At low engine speeds with minimal throttle opening, intake airspeed is greatly reduced. This lowers volumetric efficiency and engine torque. It is desirable to increase airspeed into the cylinder to reverse this effect. Camshaft lobes can be ground to counteract the low airspeed, but consequently, the engine suffers from lack of air volume at high crankshaft RPMs. A camshaft can be ground with high lift and steep opening angles to maximise air volume and large overlap to promote cylinder scavenging. However, this type of camshaft produces less low-speed torque and the engine suffers from compression losses at idle, increasing undesirable emissions. One answer to these problems is cam changing VVT. Although there are many types of cam changing systems in use, they all follow the same operating principles. This type of system uses 3 cam lobes for each pair of intake valves. Both outer lobes have the same mild profile, while the inner lobe is ground with an aggressive lift, steep ramps and substantial overlap. In this system, there are 3 rocker arms. The 2 outer arms follow the first stage cam profile, whilst the inner arm follows the second stage profile. Under low-speed engine operation, only the outer arms control valve opening. Although the centre rocker arm follows its cam profile, it does not have an effect on valve operation. When the engine speed reaches a predetermined point, the ECM controls a solenoid valve. Engine oil moves a shuttle pin to lock all 3 arms together. From this point on, the rocker arms follow the more aggressive cam profile. On deceleration, if the ECM determines that conditions are correct, it commands the solenoid valve into the release position, allowing the shuttle pin to disengage. This dual-stage cam-changing system works very well for medium speed and spirited driving. In this system, poor mixture consistency can still occur at slower crankshaft speeds due to low air intake velocity. This can be overcome by using a valve idling system. This is where only one intake valve per cylinder operates at low to moderate crankshaft speeds. The system uses a shuttle pin that can lock or unlock the intake rocker arms together. This has the added advantage of increasing turbulence, ensuring a more uniform mix of the fuel and air. The ECM monitors signals from the crankshaft position, cam position, mass airflow, throttle position, and coolant temperature sensors to determine when the shuttle pin should be unlocked, so only one valve opens. With only one valve opening, the mixture enters the cylinder at an increased velocity. This, combined with the more even distribution of the fuel charge, produces more torque and lower emissions at reduced engine RPMs. Another type of VVT found in production vehicles uses a camshaft ground for high performance and solenoid-controlled hydraulic lifters. This system can be used for valve idling, cylinder deactivation, or variable valve timing. When the ECM determines conditions are correct, a PWM control is sent to oil bleed solenoids for the hydraulic lifters. By altering the amount of oil bleed, the operating range of the lifters can be controlled, and the valve lift and duration can be managed to suit engine operating conditions. We have just looked at different types of cam changing systems. They all promote improved fuel economy, increased torque, while decreasing emissions. Thanks for watching. Bye for now.